Consumer operating systems are built to hide their mechanics. They layer intuitive graphical interfaces over the actual machine, keeping the user safe but restricted. Professional cybersecurity requires the exact opposite. You need unmediated, transparent control over the hardware itself. That level of control comes from Linux. It is a free, open-source operating system written in 1991 as a personal project by a Finnish programmer named Linus Torvalds. Torvalds shared his project with the world for free. Over the next 3 decades, it scaled from a hobbyist system into the hidden engine running the modern world, including global financial markets. Its footprint is immense. The Linux kernel operates on everything from the smartphone in your pocket to the servers on the International Space Station. When people say Linux, they are specifically referring to the Linux kernel, the core component that directly commands the hardware. Organizations built their own custom operating systems, called distributions, on top of this kernel. Examples include Ubuntu and Kali Linux. There are highly specific reasons this architecture is mandatory for cybersecurity. First, because it is open source, security researchers can inspect every single line of code for vulnerabilities. Second, it does not sandbox the administrator. It grants you total control to modify or replace any part of the system architecture as you see fit. Third is simple pragmatism. Most of the world's servers run on this architecture. Understanding how to navigate it means understanding the actual target environments you will be testing in the field. Because of this, almost all professional offensive and defensive security tools are built natively for this exact operating system. Linux proficiency provides the mandatory framework for interacting with global digital infrastructure. The first obstacle for users migrating from Windows is the file system. Windows segments data across distinct drives, like a C drive and a D drive. Linux uses a single, unified structure. Everything stems from a single origin point called the root directory, represented mathematically by a /. It is the absolute top of the architectural tree. Immediately branching off that root is the /bin directory. This houses the essential binary files and fundamental commands the system needs to function. Next is the /etc directory. This holds all the system-wide configuration files. For a security professional, /etc is a primary target. Configuration files dictate how the system behaves, and they frequently harbor sensitive data or exposed vulnerabilities. The /home directory is where regular users are assigned their own isolated personal folders. This is entirely separate from the /root directory. /root is the isolated home folder reserved specifically for the system's most powerful administrator. The /var directory stores variable data that changes over time, most notably the system log files. These logs capture a continuous record of system activity. Defensive professionals rely entirely on /var when conducting forensic investigations of cyber attacks to trace exactly what an intruder did. The /tmp directory is designated for temporary file storage. Structurally, /tmp is writable by all users. This creates a known security risk, as attackers frequently use it as a staging ground for malicious payloads. The /usr directory is straightforward. It contains the user programs and software applications. Finally, the /dev directory stores device files. In Linux, physical hardware components are represented and accessed directly through these files. Every piece of software and hardware logically branches from a single origin point. This unified hierarchy eliminates ambiguity. It allows a security professional to navigate, audit, and compromise complex systems with mathematical precision. Linux operates as a strict multi-user environment. Multiple users can operate on the same system simultaneously, with their files and settings completely segregated from one another. The base level of access is the regular user. They operate in a restricted sandbox, with permissions limited strictly to their own personal files. This contrasts directly with the root user. The root user operates with unrestricted administrative authority, possessing the capability to alter core system files and bypass all permission barriers. This binary access model introduces a foundational concept in offensive security: privilege escalation. Privilege escalation is the mechanical goal of a network intrusion. It occurs when an attacker starts with a limited regular user account and exploits system flaws to achieve absolute root control. To manage this, Linux governs access through strict file permissions. Every file dictates exactly who has the right to read it, write to it, or execute it as a program. These rights are broken down into 3 specific tiers applied to every single file: the owner, the group, and everyone else. By modifying these specific sets, an administrator dictates exactly who can interact with a given file or directory. Attackers constantly scan these matrices. They look for poorly configured write or execute permissions that will allow them to inject code. Conversely, defensive security requires rigorous, continuous auditing of these exact permissions to maintain system integrity. Cybersecurity is a battle fought over these access lines. Attackers seek paths to root, while defenders must mathematically restrict them. Consumer operating systems rely on slow, rigid graphical interfaces. Professionals abandon them entirely for the speed and power of the text-based Linux terminal. The terminal provides raw, automatable control over the entire architecture. You type a command, and the machine executes it without a graphical middleman. The terminal provides an immediate visual indicator of your access level. A $ means you are operating as a regular user. A hash symbol acts as an immediate alert. It means you currently possess root access and wield absolute system power. Operating in this environment requires understanding two vital axioms. The first is case sensitivity. A file named password.txt with a capital P is architecturally treated as a completely different file than password.txt in all lowercase. The machine makes no assumptions. The second and most powerful axiom is that everything is a file. Physical hardware devices, running software processes, and active network connections are all represented and manipulated exactly like simple text files. Finally, there is the matter of software. You do not download insecure installers from random websites. You use package managers. On Debian distributions, including Kali Linux, the standard tool is APT, which stands for Advanced Package Tool. It provides a centralized command line method for securely installing software directly from trusted repositories. Every professional action you take, from scanning networks to cracking encryption, is executed exclusively through this command line interface. Mastering the terminal and its axioms provides the essential translation layer between your intent and the operating system's raw capability. We are moving from theory to practice. Before the next module, you need to stage your hands-on lab environment. First, download VirtualBox. It is a free virtualization tool necessary for running a safe, isolated testing environment on your current machine. Next, retrieve the specific Kali Linux virtual machine image from the official Kali website. Once imported, you need the initial access credentials to log in. The default username is Kali, and the default password is also Kali. If this seems complex, do not worry. A comprehensive, step-by-step lab setup walkthrough will be provided in a dedicated future module. With the architectural map understood and your target environment staged, you possess the structural knowledge required to begin wielding live Linux commands.